Well, hello everyone. Let's solve the exercises I suggested in the forum one. Okay, I will take some notes and I will of course share the notebook and the notes with you if you want to. But I think this video should cover for it. Okay, so let's start. Okay, first we imported the libraries NumPy, Pandas, and Matplotlib. Then we read the data using the read CSV function included in Pandas. Okay. And now I suggested to create some plots in order to see what's inside the data we just opened. Okay. We can use Matplotlib. Okay. This is the most basic visualization library that we have in Python. Okay. And we can use the way I like to use it is to define the figure and each one of the graphs that we will create, and using subplots that you could also use directly plot. That's my dog drinking, and so yeah, you can also use plt.plot or scatter in our case. And we can also copy this. Okay, well, first of all, let me actually run the stuff. Okay, so we have this basic visualization using scatter. And in this visualization, I added a bit more detail. I specified the type of market that I want, and I specified the transparency I want, so that you see in here, for example, when there's overlap between each marker, you can see there's actually overlap, okay? But also you can use Seaborn. Seaborn is one of my favorite libraries, and I use it every day, and I recommend you to learn about it, okay? In my case, I used RelPlot, in which you select which columns you want to plot, okay? And then again, the same parameter to compare to see the transparency, okay? And the palette of colors and the height of the chart you want to plot, okay? If you don't specify aspect, it will be the same width and the data with which you are from which you are plotting, okay? That should cover this first point, okay? Then I propose to choose a representation for our reality. In our case, what we see in the charts is it looks suitable to use linear regression. Okay, so then let's fit a line by trial and error with changing alpha and beta. We can more or less create a fitting set of parameters. Okay. And now let's discuss a bit more about geometry. Okay. In a linear function, we have plus n. Okay. So if this is x and this is y, in our first point x1, I1, and x2, y2, okay, we can define this this value, which is the slope, okay, which is the tangent of the angle alpha, okay. Let's not call it alpha, since we are using alpha for parameters. Let's call it gamma. Okay, and n, which is the intercept, okay, and that means the value at which our line crosses the y-axis, okay? So by choosing these parameters, intercept, we have defined our linear function, okay? So that's exactly what I did, and looped through a set of alphas and a set of betas so that we create a set of representations from 1 to 16, and I stored them in a dictionary. Okay, so this dictionary includes as keys the name of the representation, and as values another dictionary including the names and the values of these alpha and beta parameters. Okay, if we plot this or if we include these representations in our data frame, you can see it looks like this. Okay. So now let's plot each one of these representations against the reality that I shared with you, included in the original data set. Okay. Again, I used a for loop. Okay, and I am looping through each representation included in the keys of the dictionary, which are rep1, rep2, rep3, and so on. Okay, and for each one of these representations, what I am doing is taking the parameters that are associated with that representation, calculating our linear regression, okay, and then plotting our reality, our actual values, against our representation, okay, and then of course plotting the legend. And you can see it looks like this, okay. This is a way to do it. There are many ways to do it. You guys tried different ones. They are just as good as this one, okay? There is no correct answer here. Then we started evaluating our representations using mean squared error. I created this function in order to calculate the mean squared error. Let me write again what this is. Mean squared error equals the sum of each squared residual, okay? This symmetry goes from 1 to n, being n the number of observations in our data, okay? So having created this function called mean squared error, we can check how good is our representation, okay? Also, I proposed to create or to do the same as this function does, but just in one line, and I suggested using reduce and lambda. Okay, I know that you have already seen these reduce functions in your Python course. Okay, so here I am applying two of your suggestions, guys, two of your colleagues' suggestions. In the first approach, I'm using Diaz, I don't really know how to pronounce it. And she suggested this clever use of NumPy functions. Okay, let's break it apart into its parts. Okay, first of all, she used this NumPy subtract, which basically receives two lists, two arrays. And for each element, it calculates the difference. Element 1 minus element 1, element 2 minus element 2, and so on. Then, well, let's plot this. Let's see how it looks like. Then she squared each value in that array. Or he, I don't really know. Sorry. In my lack of knowledge, I assumed it's a woman's name, so I don't really know. Sorry there. And then again, for calculating the squared values, that we have calculating the squared values of the difference we had just calculated, we are applying square to all these values. Okay, let's see how it goes. Okay, it looks decent. Okay. And then if we apply reduce to this list or to this array, basically what we are doing is for each two elements in that list, we are summing them and then storing that value and adding it to the next value in the list until all the list is run through. And then we divide it by the total length in order to calculate the MSE, which, by the way, I was missing. 1 divided by n. Okay. So this is one way of doing it, using NumPy functions within your reduce and using lambda for summing up each pair of values. But also we can use list comprehension using zip as well, as your colleague Göktuğ. This Göktuğ sounds Turkish, I think. Yeah, right, it's Turkish. And again, using lambda within reduce, okay? So what I'm doing is, let me first break this. Okay, so you know list comprehensions in Python, which this list comprehension, what I'm doing is first zipping the two lists or the two arrays together, and for each pair of this, in this iterator, in this zip, I am taking the first value, I am subtracting the second value, okay, and I'm squaring that difference, okay, and then again applying summation with lambda and reduce, and dividing between the total length of your target feature. Okay, so if we do this, we have 282, and if we do this, we have 282. Okay, they are the same, and these are two magnificent ways to calculate this MSE with just one line of code. Then what I did is to calculate for each representation, calculate each MSE using this for loop again. We could have used, for example, a list comprehension or dict comprehension. This is up to you to learn, to try how to do it. And this is the end result, okay? So the next exercise, what I was asking is, what's the best combination that we can find of alpha and beta according to the MSE, okay? So what I did is to create a function that takes as arguments the evaluations dict, which is this dictionary here, and also the representations dict, which is this dictionary here, okay? So first, what we are gonna do is calculate in this dictionary here, in this evaluations dict, we're gonna calculate which is the key that has the minimum value, okay? We can do that by using the min native function in Python and passing this key, okay? This key is we are basically telling the min function how we want to compare the values, because we are passing a dictionary, okay? So this is the way to calculate the minimum key that, or the key that holds the minimum value in a dictionary. When we have this key, we pass this key to the original dictionary of representation, and we save the best parameters. By doing this, it fails because I didn't run this cell, because, okay, I didn't run the representations dictionary either. So let's do it. Here they are. Now I can run the next ones. Oh, I forgot about MSE. Here it is. Okay, now we have everything. And now we can calculate the optimal set of parameters that minimize the MSE. Okay, according to the original representations, this is the pair of representations that hold the minimum MSE. Okay. Now in the next step, I was suggesting how low can this MSE value go. Okay, and what I did again is to create a set of alphas and betas. Okay, and defining a step. This step is basically the difference between each one of the values in the alphas and betas. Okay, Also, what I did is to create an empty matrix filled with zeros that will hold some values that I will explain in a moment. Okay. Also, I set this best representation dictionary as our ground truth, as our baseline, and this is the representation with which I will be comparing each result in the loop, so that we can know if it's better or not. If it's better, then the latest representation will be saved in this value, okay? And if not, we will move to the next loop, okay? So for each alpha and beta in these ranges here, I am calculating the estimation, I am calculating the MSE, and I am saving in that matrix that I created the value of MSE, okay? If you see the indices here, I and J, index I represents the alpha, index J represents beta, okay? So basically what I am creating is I'm creating a matrix that for each alpha and beta holds the MSE, so that we can visualize with a heat map how MSE evolves when alpha and beta evolves, okay? And then once we have calculated the MSE, I compare if that MSE is better than the one that I set as the initial MSE, okay? As a trick, use an initial MSE that is quite high so that you are certain that you will start from a safe position, okay? And if that happens, if the MSE that we just calculated is better than the one I assumed, then the new best representation will be the one that I just created, okay? So if we plot this, again, I am plotting using a scatter plot and a normal line plot for our representation, and the heat map using Seaborn again, okay? This library is quite useful, and I really recommend you to get the gist of it and to play with it so that you are familiar with it, okay? By doing so, we have here on the left side the best representation with the scatter plot of our actual values and the line that yielded and the set of parameters that yielded the best fitting representation of this data, plus our heat map. As you can see here, well, I changed the axis, but you see the idea. On the vertical axis, we have the alphas. On the horizontal axis, we have betas, and we see the evolution graphically of MSE, okay? I would say that the lowest value is around here on the darkest areas, according to the scale. So I would say it's here, 280, 279. So here is the minimum value we can find of MSE. And as the following exercise, and I think it was the last one, what I asked is to create a single function that receives x and y and the size of the step and yields our representation and the MSE of that representation, okay? So what I did here as a starting point is to first eyeball a value for alpha and beta in order to have a baseline, okay? And for this, what I did is just apply exactly that, the basics. Oh, sorry, the basics of our linear function. I just realized that it might have been like this for a while, but you get the gist of it. Ask me some questions next day in class. Sorry. And so yeah, let's see how I did this eyeballing of alpha and beta. So basically what I did is, if we have these values here, I am assuming that, or this is x, this is y, this is x0, y0, and if this is yn, xn, meaning the last one in the list, okay? What I am assuming is that the initial slope is going to be the change in y divided by the change in x. So that is yn minus y0 divided by xn minus x0, okay? And this is the value I assumed as the approximation of alpha. And for beta, what I did is basically taking this value here, okay, as an initial estimation. So once we have this initial estimation, I created a range on the size of these two. So approx alpha and approx beta, plus minus. In the case of alpha, I used plus minus 1. In the case of beta, plus minus 5. This is the range of values we will be looping through in order to calculate the best representation. Again, I copied what I did in the previous cell in here, okay? And I calculated MSE. If that MSE is better than the previously saved one, I will take that as the next best one, and then I will return these values. So let's test our function. It works, apparently. Well, it's looping through all the values that we set. Okay, it's done. And it gives us our prediction and our MSE. So that's all. I will upload this notebook and this notes. And I'll send you the link for this video as well. And yeah, more videos are coming to explain about well, the open questions. And let's talk for the forum too. Okay. Thank you.